Yes. Yeah. So welcome again for our monthly meeting. This month, Mr. Ravin from TGT company will discuss tube integrity using their advanced wireline tool. Beforehand, just I will introduce myself. My name is Mazen Hilali, currently the chairperson of SPWLA Iraq. We are right now holding a monthly meeting each month. And from our committee, Dr. Mohammed, he just want to welcome our guest, Dr. Mohammed.
Yes, Mr. Mazen. Hello, everybody. My name is Mohammed. I'm Vice President of Technology SPWLA Iraq Chapter. SPWLA Iraq Chapter 2023 theme focus on integrity. Would like to introduce the third webinar today in our meeting with you. The webinar will be named Tube Integrity TGT Company. Welcome everybody. Welcome to Mr. Ravin, who will be our lecturer today, and nice to meet you again, Mr. Ravin. Hope the best for everybody in our meeting. Thank you.
Thank you, Dr. Mohammed. And before we start, we'll just take 1 minute from Mr. Ravin time and lecture just to show our attendees our plan for this year. Just I will share my screen. Okay. Sharing. Okay. Yeah, you can see my screen?
Yes,
Hello?
yes, very clear.
Yes.
Clear. Okay. So as Dr. Mohammed mentioned, our theme for this year is to focus on integrity. Next year will be another theme. This webinar will be, sorry, it's about tube integrity. We'll correct this one by TGT company. Our plan for this year this is our first year, we'll hold like one webinar per month, and most probably there will be like a meeting, like workshop meeting for about integrity, maybe in December or November. We'll discuss about this one with the petrophysicist of Iraq. This is our third webinar. Next month actually will be EVCAM webinar. We'll podcast about this one later. We plan to do like a special phone number, like Facebook page and the Telegram page, business, WhatsApp business also for easier communication. For this year, we'll have more meeting from Kappa, EVCAM, as mentioned, GeoActive, which is IP company software, to meeting, and with scientific drilling about casing inspection in high temperature wells. There will be an initiative like a special certificate for attendees that attend 6 webinar or more per year. It's called like a super learner certificate for the attendees. Also, I saw many people like they are member of SPWLA, but they join like Qatar, Saudi, something, but they work in Iraq industry. So please, if you are working in Iraq, we really appreciate to change your location. And we'll send the link later how to change the location. It's very easy. Okay, that's all from my side, and I will give the mic to Mr. Ravin. You can start.
Thank you, Mazin, for the introduction. I just want to confirm that everybody can see my screen and hear my voice properly.
Yes, just sorry, before we start, I'd like to introduce Mr. Ravin. He's the domain champion for TGT company. You are based in Dubai or Kuwait? Kuwait. He's based in Kuwait, responsible for all interpretation, geoscience, advanced interpretation for TGT tool in Iraq and Middle East. Okay, this is his second webinar, and we appreciate his support for second webinar with Iraq SPWLA. Okay, and we also always appreciate TGT support. Thank you so much.
Thank you, Mazin, for the nice introduction, and thank you, Dr. Mohammed, for the introductory speech. Appreciate it. So I hope everybody can see my screen and hear my voice clearly.
Yes.
Perfect. So today's webinar, I want to welcome everyone to today's webinar. Today's webinar is about tube integrity. We had the first webinar based called Seal Integrity, and this is the second part of the integrity services that TGT provide called Tube Integrity. So Seal Integrity, for the people who were not able to join the first webinar, is just to identify if the elements that are supposed to seal in a weld system are sealing or not, like the packer, the casing, the tubing, the cement. Are these elements which are supposed to keep the weld system integral, are they actually sealing or not? That's the purpose of seal integrity. Now, coming on to tube integrity, the single sentence definition would be barrier by barrier assessment of multiple tubulars from a single through tubing deployment. And this is probably, if you have to take one sentence out of the whole presentation today, I wish it would be this sentence, that what is the final output that we get from tube integrity? We get individual assessment of not one barrier, but multiple barriers by a single run. So the advantage of the technology compared to conventional techniques, how the technique uses the electromagnetic mechanism to identify the metal loss, and some case studies. This will be the topic of discussions in today's webinar. So first of all, I will introduce the concept of tube integrity. Why is it necessary? The working principle of electromagnetic tool, which helps us to do this assessment of multiple tubulars. How do we do it? What's the method of thickness calculations? Some case studies and summary. Please feel free to ask your questions in the end. Right. So if you remember this picture from the previous webinar, basically this is the picture of a weld system, right? The ideal scenario, we have a perforation with our hydrocarbon coming from the perforated layer going all the way. Unfortunately, this is not like always the perfect case, right? Sometimes the seal, which is the cement in this case, you can see it's not sealing, and this seal is leaking, and the unwanted gas flow through the poor cement and goes all the way, which creates a sustained endless pressure at the surface. Another problem that can happen is this flow, this continuous flow, creates a metal loss, which will lead into a hole and create a barrier leak. And now aquifer, which is usually in the shallow layers, or probably even near the perforations as well, these aquifers have corrosive properties, and this create corrosion in the metal. So because of this unwanted migration, and the life of the well creates the metal to be corroded, and this is what is we are assessing using tube integrity. This is why we need to do multi-tube integrity to identify not just the condition of the first barrier, but the second, third barrier, and probably beyond as well. So what pulse the electromagnetic tool of TGT provides is individual barrier by barrier assessment of multiple tubulars up to 4 tubulars. So the advantage of the technology is that compared to conventional techniques like multi-finger caliper, if you have to assess the condition of the tubular, for example, if you have to assess the condition of tubing, you have the tubing is there, and you run the tool and you assess the condition, internal condition of the tubular. If you have to assess the casing, with the first casing, you have to literally pull out the tubing to assess the condition of the second barrier, and that too, you assess only the internal diameter. The advantage of the electromagnetic pulse technology is that you can deploy the electromagnetic tool through the tubing, and you can assess what is the condition of not just the tubular, but multiple casings beyond. And the added advantage is that there are multiple added advantages. It's not the internal diameter that you're assessing, since the electromagnetic is capable to identify what is the condition of the outside wall. You can assess what is, if there is any external metal loss as well. So these are the advantages. So let me take you through the working principle of the tool. So I'm taking a Pulse 3 as an example here to explain the theory part. So basically Pulse 3 is the TGT technology which helps us to identify first, second, and third barrier. So in Pulse 3, we have three sensors. So it is an active tool. There are three sensors. There is a short sensor, a medium sensor, and the long sensor. So the name of the sensor, as you can see, is derived from the length of the sensor itself. The short sensor is only 5 inches, the medium sensor is 13 inches, and the long sensor is 19 inches. So based on the length of this is the scanning radius of the tool itself. As you can imagine, the short sensor mostly scans the first barrier, medium sensor scans the first and second, the long sensor scans the first, second, and the third barrier, right? So each sensor, inside each sensor, there is a generator and a receiving coil. And the generating coil magnetizes the metal around it, and the receiver coil sees how the decay of this electromagnetic effect is, and we assess the decay to identify the metal condition. So let me take you to the principle. Let's look at a typical well scenario. And we have the tool inside the well. You can see the tool. Imagine this is the first barrier, this is the second barrier, and this is the third barrier. Now, as you see before, there are three sensors. So the first barrier, it scans the first tubing. The second sensor or the medium sensor scans the first and second casing, and the long sensor, it scans the first, second, and the third barrier. So, as I mentioned before, we have a generator and receiving coil. How it functions, the generator sends a square electromagnetic pulse, and the receiver sees how the decay is with respect to time for this electromagnetic current. So what we do is we record the data of the decay in multiple time points, and we analyze.
Sorry, Ravin. Sorry
Yes.
to interrupt you. Can you change your network or something? Okay, like your voice is going back.
Okay.
Maybe if you have like, I'm not sure if you are on Wi-Fi or 3G.
I am
or
on Wi-Fi. Okay, maybe if I switch off my Wi-Fi and switch it on again, I'll be out of the meeting. So you want me to get out of the meeting and come back again?
No problem. No problem.
Yeah.
Okay.
All
At
right. So
least
let me.
we'll have a. Yes,
Perfect.
please.
Right. So let me switch off my Wi-Fi and come back.
Hello, Nicholas. So, Ravin, voice is clear at your end?
For me, it's very clear.
Okay. This is good. So maybe this is my network. Okay, no problem. He will come back shortly. Yeah, you back, Ravin? Yes.
Yes, I'm back. Is it better now?
Yes. Yeah. Some
Okay.
other people said they can receive you very clearly, so maybe
Okay.
it's my network. I'm not sure.
Okay. All right.
Okay.
Okay. I hope it's
So
better
yeah,
now. I'll just switch off my camera just to save the
bandwidth. Yes. Okay.
Wi-Fi. Yeah. Perfect.
Okay.
Right. So
Yeah,
let me
please continue.
continue. Sorry, everyone. Apologize for the inconvenience. So basically,
Okay.
as I was mentioning, there is a generator and receiver, and the receiver sees how the decay is with respect to time. So you can see the plot here, and we take the data at multiple time points, and we analyze this data to see how the decay is. So let me show you one example of how the data looks like from one of the sensors and explain to you how we can analyze this decay data to understand more about the condition of the metal. So this, we use the time domain technique. Let me show you how the data looks like. So in the y-axis, we have amplitude. This is the energy, and this is the time. And this is the electromagnetic decay response from the short sensor. If you remember, the short sensor scans the first value, right? So how the data would look like for a thickness which is nominal without any change. This is how the typical data could look like for a situation where there is no change in metal. So this is like a baseline decay, right? If there is more metal, this is in the case of a coil, because across the coil there are two tubulars connected. This means there is extra metal. The decay will be much slower compared to the nominal thickness. Why? Because now instead of a single nominal thickness, there is a double collar, a double metal thickness because of the collar, and this makes the decay become slower. Now, what we are actually looking at in a well using tube integrity is the metal loss, right? And what would happen in the place of a metal loss? Across the metal loss, of course, there will be less metal, and this would lead to a faster decay, as you can see in the red line. So what we are looking at from the decay response is for the faster decay to understand that across this particular depth, there is less metal. That's why we have a faster decay compared to a conventional decay. And this is the ultimate principle behind electromagnetic thickness detection. And this is the running principle, how we identify the metal losses in multiple tubulars. Now, since we have the data from not just the short sensor, I will show you how the data looks like for the medium sensor. Now, the interesting aspect is that if you look at the y-axis, you can see the time ranges from 0 second all the way to 0.08 seconds. This is the data from the short sensor. Now for the medium sensor, you can see the major decay for the second barrier happens at a later time than the short sensor. It is this principle of the time domain technique that we use to identify the thickness of not just the first barrier, but the second, third barrier, and beyond that in some cases, right? So you can see that initially across the initial time that there is no change, but across the second barrier, you can see that there are, across the defect, you can see a faster decay, and across the collar, you can see a slower decay. Now, this is for the second barrier. Now, across the third barrier, if you look at the time, you can see it's a much further later time than the medium sensor and the short sensor. We use this technique to identify the thickness of the third barrier, usually is 1338 casing, right? So this is the running principle behind electromagnetic thickness detection. We use the electromagnetic decay to understand how much of metal is there, and if there is more metal, the decay will be slower. If there is less metal, the decay will be faster. And we use Maxwell's equation in this data to convert this electromagnetic decay data into thickness. And that's what we finally deliver to the customer. So let's look at a raw data response, how it looks like. So this is the data from the multiple time points, and these three logs represents the data, how it looks like for this individual tubing size. So for each tubing size, we have a template of which time channels would represent the decay for that, and we use that basis study to analyze that particular time channel for interpretation. So basically, you can see this is the response, and you can see the slower decay, the slower decay across the collar. You can see here, And across the corrosions, for example, in this particular case, for 9 fiber 8 casing, you can see a faster decay. This is the second place with the metal loss. This is why it's a simple analysis magnetic tools. So individually, we can analyze the first, second, and third barrier. There are some technologies which will give you a total thickness of multiple tubulars, and you are not able to differentiate between where is the metal losses in the first, second, or third barrier. But with time domain technique, the beauty is that we can analyze what's the situation for the first, second, and third barrier individually. Right? So that's the raw response. And after solving Maxwell's equation, we can identify the thickness. And as an end product, what we can deliver is a joint by joint analysis of the well for each individual barrier. So let me show you the summary table, how it looks like. So we can, in the column, we have the joint number, what's the top of the joint, the length of each joint, what's the nominal thickness which is provided, what's the minimum thickness, what's the average metal loss in that particular joint, what's the maximum metal loss, at what depth is the metal loss maximum. So you can pinpoint for your workovers, okay, at this particular depth, I have the maximum metal loss. So during workover, if I'm going to put a patch or something, I have to actually care for this exact depth to put the patch. We are after discussing with the client, we actually come up with a class of hazard because the client knows more deeply about the kind of metal loss that's expected in the region. So we categorize the metal loss into multiple categories to come up with actionable, like quick look actionable solutions for the client. So about 25%, mostly the clients, they recognize as a significant class of metal loss, and it's something to be taken care of. So that's the final summary table that's provided. So for each individual barrier, we can understand by a quick look which are the joints which have significant metal loss, which are the joints which have light metal loss, and so on and so forth. So for Pulse 3, you can see a tabular column of the specifications of the tool. The maximum temperature rating is 150 degrees Celsius, and pressure rating is 14,500 psi. It has an H2S resistance of up to 30%. And we can identify the accuracy. The accuracy is different for each barrier. So the first barrier, it's plus or minus 3.5%, 6% for the second, and the third barrier, it's plus or minus 12%. So since the tool is very slim, it's 1.65 inches only, we can assess almost all tubulars and almost all the type restrictions we are able to pass through. The conveyance, it can be done rigorously, so it can be done in slick line, wire line, coil tubing, and tractor, and so on. So these are the specifications of the tool, and we have a latest technology called Pulse 1. So what is the added advantage of Pulse 1?
What was the length? What was the length of this tool?
So it's approximately, I think it comes around 6 feet. If I'm not wrong, it's around 6 feet. For Pulse 3. So it depends on tool by tool, so it's approximately 6 feet, yeah.
Okay, thank you.
Right, so we have the latest technology called Pulse 1. So Pulse 1 gives you a sectoral understanding of the electromagnetic condition. So basically, Pulse 3 and other electromagnetic technologies give you like a circumferential average of the metal loss, but Pulse 1 has 8 electromagnetic sensors throughout, and we can understand sectorally how does the metal loss look like for the first barrier. So it gives you sector-wise how the thickness would look like, and it helps us to identify concentrated metal losses in one area of the tubing, or if it's like evenly spread across. So it gives us a much clearer understanding about the condition of the well. It gives us a sense of all around how does it look like in a 360-degree view of the first barrier condition. So the advantages of the conventional technique is that, especially for Pulse 1, it gives a true wall thickness in 8 sectors. With Pulse 3, Pulse 2, and Pulse 4, we can identify what's the circumferentially, or it will average of the metal loss. We cannot understand individually by sectors, but like circumferentially average, we can understand what is the condition. Pulse 1 has the ability for all-around sensing. The another biggest added advantage is that compared to conventional techniques is that these are non-scratch contacts. So like multifinger calipers, which scratches the internal diameter of the walls of the tubing, the electromagnetic technology does not have this problem. And it's said that this scratching actually exaggerates, creates like this corrosion to come faster in some of the wells in some cases, because it scratches and creates like a catalyst for corrosion to like really grow. So this is avoided by using electromagnetic technology. And another advantage is in chrome completions, it can be used. So the dead time of the tool is very low. So in chrome completions also it can be used. Compared to conventional techniques, if there is any deposits, it's insensitive to such conditions because we are magnetizing the metal and seeing how the decay looks like. It's insensitive to surface deposits, and it helps to understand even if there is a metal loss and there is deposit on top of it, which could be missed in conventional caliper technique. Using electromagnetic technology, this can be very clearly identified. Now, another big advantage is that its ability to see not just internal metal loss, but external metal loss as well. Even though it cannot differentiate between them, the technology will be able to identify if a metal loss exists not only internally, but externally as well. Now, the next advantage is that there is no need to pull out the tubing to understand what's the condition of the 9/5/8 casing. So one single tool will be able to identify what is the condition of multiple barriers. The well need not be shortened. The well can be flowing. It's not affected by what's inside the tubing. So all these are the advantages of the electromagnetic technology over the conventional techniques that are available. Right. So let me show you, I explained the principle. Let me show you how we capture the data to get this results. It's very simple. The data capturing method is very simple. We prefer to record the data during up pass. So we have a stable speed, running speed. So we run and hold with high speed, and we go up recording the data in a stable speed with ranging from 12 to 18 feet, because the sensitivity depends upon the speed that we run. So slower the speed, we get better, more reliable data and better sensitivity of the data. So it's a very simple technique of data acquisition. We run and hold at high speed and pull out of whole recording data. So that's the method in which we acquire the data. And let me show you some case studies and explain to you what are some of the added advantages of the technology in real world scenarios. So the first case is in which we identified through hole corrosion in one of the wells, and this is actually an SPE paper as well. We can see the SPE paper number here. It's a paper we wrote with QC. So from left to right, we have the depth panel. This is called the delta panel. I have just shown you the raw responses, and delta panel helps us to visualize the raw responses in a different way. It helps us to very quickly identify the colors and the corrosions. So it's just mathematically we are using averaging the raw responses and coloring it based on the average. If the response is the decay is much lower, we give it as a blue color, which, as you already know, is for colors. So if you see a blue color in the delta panel, it usually relates to the color. So here 1, 2, 3, and 4. These are the colors of the tubing. And if the decay is much faster, we give it as a red color or a brown color. And here you can see that it has identified a brown color here. Excuse me, brown color here, which identifies here there is a metal loss, and we have calculated it, the metal loss, exact metal loss in the tubing. It's calculated to be around 30%. And this is the thickness of 3.5-inch tubing. Here we have the far delta calculated from the long sensor, and here you can see the similar metal loss identified here. So in the delta panel, as you know, like we have the short sensor and the medium sensor, and since the medium sensor scans not just the first barrier, the second barrier also, we can see the metal loss in the first barrier, even in the medium sensor. This is why excuse me, you can see the red color in the far delta panel as well. This gives us a double confirmation about the metal loss in the first barrier. So we have identified the metal loss here in the first barrier. The good part is that we know that this metal loss is not in the second barrier. We can see there is no effect, a brown color effect across the corrosion response for the second barrier. This means that this effect is only across the first barrier only, and this is one of the advantages of the time domain technique, that we are able to differentiate the metal loss is in the first barrier and second barrier. Even if it's in the both barrier, we are able to identify this metal loss.
So
Another additional yes.
Yeah, so
Excuse
this one
me?
is not giving, yeah, it's not giving only the thickness, it's giving only full map, like a 3D map.
I wouldn't say like 3D map is a bit like
or 2D
more,
map. Okay.
Yes. I think 3D is a bit too much, and we can provide it only with Pulse 1. But this is Pulse 3, and I would say this is like a 2D map. By sectoral average, we can see that there is a metal loss. In this circumferentially, there is a metal loss in that depth. That's what we can identify.
It's because the normal tool we saw
Security.
usually is give only thickness. I believe Mr. Abbas have a question.
Yes.
After you finish, Mr. Mazen, after you finish.
Yeah, I'm finished. Okay, you can proceed.
Thank you. This temperature log already run with this tool?
Yes, you're right.
From
yes,
where
so
get this temperature gradient?
Yeah, so basically we, as you saw, like the program, we have a run and hold and up pass recording the corrosion data. And this temperature is during the run and hold. So we are recording temperature as well. So if there is a hold, sometimes that there is a big temperature gradient change, and this is what we utilize for analysis along with the corrosion data. So here we have a 30% metal loss identified in the tubing, plus we have a temperature gradient change. So this is like a double confirmation for us that there is a most possibly a hole at that depth, which is what we identified after we pull out the tubing.
But temperature log cannot record after 3 or 2 barriers. This is my question.
Yeah, so temperature, this is a good point. So basically, temperature
Therefore, temperature log for many barriers, this is not reference. Because now you have tubing, then casing number 1, casing number 2, each one you have cement. How to get this temperature log reference to confirmation about there's some problem in material loss with the TGT?
Thank you. That's very good point. So basically, as you said,
because
yes,
always, for example, for these tools, maybe this temperature log from BLT, not from this, and do much for it, because this is not run with temperature log. The MIT log, for example, MIT, ETT, MTD, not run with temperature log.
Right. So basically, from TGT side, we make it as best practice to run temperature along with electromagnetic survey. Why? Because as you mentioned, as you correctly mentioned, temperature reacts to multiple things. It's not just reacts to what's happening in the tubing or casing. Temperature reacts to multiple things. So how we used it in this particular case is that from the electromagnetic survey, I know that there is a 30% metal loss. Now, 30% metal loss is big, right? But since this is pulse, it can just give the circumferential average of the metal loss at that depth. This metal loss could be at one point in that depth, or it's averaged in 360 degree at that depth, right? Now, I know that there is 30% metal loss, which is a fact from electromagnetic. Now, if I have the temperature sensor along with the tool set of electromagnetic, this is a separate sensor, I install it. So I have the sensor and I have this data during run and hold, and I see a gradient change, and I know from my electromagnetic survey that there is a 30% metal loss. I'm just correlating both of them to come to a conclusion that this gradient change could be because of the hole in tubing, which created a gradient change. So it's not necessarily that it's because of that. I'm just correlating data from two sensors, which helps me to come to a logical conclusion, and that's it. I hope I was clear.
And I have a small comment as well. Thank you very much, Vishnu. Yes, TGT, it's a bit different company. We are not running tools from any third-party company. We're not running MTT or MIT, something else. So we are manufacturing tools from A to Z, and for us, it's very easy to add additional temperature module. So we just like coming one module, which is like 1 feet, and we can put this module to any string. So it's not a big deal for us. We have such practice in some of the countries we are running combined in same string. We can add any module, anytime, any position. And most of the times we're adding temperature as well.
Mr. Abbas, did we answer your question?
No, after finish, I have another question. After you finish.
Okay, no problem. No
Thank you.
problem. Anybody else? Anybody else?
Yes,
Oh.
there is two questions in the chat. There is two questions
Okay.
from Lamris and Nicholas.
Can you please read, because I cannot see the question. Mazen, could you please read the question out for me? I cannot see what's written.
Thank you, Rafen. This is Lambris speaking here. My question is about how this tool measures the external metal loss. Was it measured by the medium sensor for the first tubing and following the longest sensor for the second and so on?
Right. Thank you, Lambris, for that question. So the electromagnetic technology, as you mentioned, has short sensor, medium sensor, and long sensor. Now, each sensor is dedicated for each barrier, right? So the short sensor for the second barrier, medium sensor for the first and second barrier, it concentrates mostly on the second barrier, and the long sensor, extra long sensor for the third barrier. Now, the purpose of the first barrier is to scan for the first, for short sensor is to scan for the first barrier only. Now, it's by principle of the technology that it just sees how the decay is. Now, how the decay is, it could be because of the metal loss, either inside the tubing or externally. It's sensitive to just metal loss. It doesn't know if it's internally or externally. So if I see a metal loss, I know that there is a metal loss at this particular depth in this particular barrier. But I don't know if it is internal or external. If I have to know this, I can just club my tools with multi-finger caliper, and multi-finger caliper will also tell me that at this particular depth, there is a metal loss. If both of them say that there is a metal loss, then this is internal. If electromagnetic says that there is metal loss, but caliper does not say, this is an external metal loss. So we can use this technique of combining multiple tools to come understand if it's an internal or external metal loss, but electromagnetic technology by itself cannot differentiate them, but it's sensitive to both.
Okay, so it's meaning the metal loss is the average, or we can say it's like sectoral. So
100%.
do we need to run MIT, I mean the caliper log, including, I mean, in this pulse tool as well?
That's a great question. Thank you, Lambris. So basically, as best practice, some clients, they are very particular in understanding if the metal loss is internal or external. And in that cases, it's recommended to run MFC with electromagnetic so we can differentiate the metal loss is internal or external. But eventually, what both the tools are telling you is the condition of the metal. One is a physical tool touching, and are telling you that internally there is a metal loss, and second uses electromagnetic technology. So it's really up to the customer to know to like the amount of information they want, like to what extent information they want. If it's really necessary to know internal and external metal loss and differentiate them, it's recommended to run both. Otherwise, if your requirement is to understand only the metal loss, electromagnetic is more than enough, because compared to MFC, multi-finger caliper, it can see not just internal but external metal loss as well.
Okay, thank you, Mr. Rafen. It's clear now. Thank
you very much.
Yeah, and Nicholas from Kava Company is asking, the wall sketch is showing eccentric tubing, which is true, look like it's eccentric. Is this tool can handle eccentric eccentric tubings in your analytical calculation?
Yeah, thank you for that question. Yes, we can take into account of eccentricity. We have advanced filters to remove eccentricity and eccentric data of tube eccentricity and tool inside. We have centralizers to keep the tool concentric inside the tubing, but tubing to tool eccentricity and to tubing to casing eccentricity can be taken into account using the filters and analysis.
Hopefully this answers Nicholas' question. So you can proceed, please.
Thank you very much. So for this particular case, we pulled out the tubing and we found out that there is actually a hole inside the tubing, and it was very important for the client to know this information, and we wrote an SP paper about this particular case, which was a very successful case for KOC. Right. So moving on to case study 2, this is another very interesting case, right? So this, let me tell you the story for this case. So the client had an issue with pump overheating. So the well was a producer with the ESP pump, and the pump was getting overheated, and the client was interested to know why the pump was getting overheated and what is the reason for it. So it was decided to run, and they suspected some problem with the tubing. They believe there is a hole in the tubing which is creating kind of a recirculation, and they wanted to confirm this theory that there is a recirculation which is causing the pump to overheat, right? So basically, TGT was asked to run not just our electromagnetic survey, but our noise survey as well. So what we did is that we run as 2 separate passes our electromagnetic survey and temperature and noise to confirm the theory of the tubing leak, and to understand at which place exactly is the tubing leak and what could have caused this tubing leak which created this recirculation, right? So from left to right, we have the depth panel. This is the thickness which was built from the short sensor for the 3.5 inch. You can see that from 0 to 0.5 is the nominal thickness, and you can see that decrease shows a metal loss, and here you can see the spikes as the chords, right? So you can see throughout there is a multiple huge metal losses which were identified in 3.5 inch tubing. In the next column is the thickness for 9.5 by casing. We can see even bigger metal losses at this particular depth. And this is the thickness for 1338. We can see even bigger metal losses. So just by looking at the thickness logs, we can understand or come to a conclusion that there is some highly corrosive fluid or elements in this particular area, and this is actually eating the casing from outside to inside, and which is actually so there this outside casings are heavily corroded. 1338, 9.5 by A is starting to be heavily corroded, and it actually reached the 3.5 inch tubing. We have the well sketch here. We have plotted all the corrosions in red color. Then we have the temperature recorded along with our corrosion survey, and we have the noise survey also. So we did the noise during flowing, and you can see a humongous change in temperature gradient across this particular depth, where we found out a maximum corrosion in the tubing. So we correlated to the tubing leak, and you can see the noise log also clearly shows a big spike here. Is the recirculation of the produced fluid that's happening here. So combining all the technologies give us a full understanding about what's happening in the well. So why it was very necessary to run the electromagnetic survey in this well. If we run only the temperature and noise, we would have still identified the the leak point here and still be able to fix this well. Why it was important to run electromagnetic survey? If we run only noise survey, we will know that there is a temperature gradient change and the noise here, and we will correlate it to the tubing leak here. But we would never know what is causing this. This is a big problem. Now, if I fix this tubing and if I put a patch, now I don't know that there is a huge corrosion in outside casing which is eating
sorry,
from
Ravin.
outside.
Yeah, because of lag. What is the leaking depth? What is the depth?
It's around 1,600.
Above
Yeah.
above
Okay.
ESP, right? Above ESP.
Above, yes, above ESP, if you can see my red pointer at 1,600 feet.
Yeah, actually, your red pointer is disappearing and back, so we cannot see. So if you mention the depth, it will be much easier for us.
1,600 feet.
Put your pointer, please. We didn't see your pointer. Where is? Because our eyes not good to see where is the depth. Anyway, above ESP, right?
Above ESP,
with the
yes.
with the temperature change. Okay.
Yes, exactly.
With the blue temperature change. Okay.
Correct. Exactly. And if you look at the 3.5-inch tubing thickness, you can see at that exact depth where the temperature sharp changes, you can see there is a big spike in the metal loss in 3.5-inch tubing also. And since we had the electromagnetic survey, we knew the full picture and we understood that there is something eating the well from outside. And for fixing it for the long term, we not just have to pull the tubing and change it, we have to do something about the casing corrosion as well. So probably we have to put a liner all the way up or something. So the solutions are multiple, but anyway, we not just understood what exactly is the problem here, the reason for pump overheating, but we with using multiple technologies, we were able to plan the workover well ahead and much in advance because we knew the full picture, so we could take the right decision so that the issue does not repeat itself in the future as well. So combining multiple technologies provide great value, and this particular case help us to understand the full picture, which help us to solve future problems as well.
Excuse me,
This
I
is
have one question.
Yes, please.
Sure, when you run this tool during the production, right?
Both shut-in and production. So the red color, the temperature is from the shut-in, and the blue is from production.
Your tool with SNL run together, right?
Separate passes, yes.
Separate pass or run together? Because according to the procedure for each tool difference. This is my question.
Separate passes.
Separately. We run SNL during the production, right?
Correct.
Yeah, flowing. Yeah, SNL flowing.
Flowing. What about the cement behind casing? Is good or bad?
Cement behind casing.
Yes.
Because there was no objective to assess the condition of cement behind casing. The objective was to check.
Because the one limitation for the SNL, if you need check some channel or fracture or anything behind casing, you should the cement is very good to check the any move for any fluid behind casing. You should the cement is very good.
Correct.
This is a principle for SNL.
Correct. So in this particular case, that was not the objective. So if
sometimes many person when run SNL during the casing or during the tubing, he didn't check the cement. When he sees some noise from behind casing, he thinking this is channel. Okay, this is a fracture, but he didn't check the cement actually.
Right. So
my question clear?
Not really. So you said did we check the cement quality in this particular case?
Because I do many cases for SNL in my field. If the cement is very good, give me very good result. If the cement not good, also the company he refuse run the casing. Also my advice for any company didn't run any SNL with the poor cement.
So you are saying if there is poor
confused
cement
for our result for future.
Right. So as I understood, let me rephrase your question. So you're saying if the cement is poor, there is no value in running the noise. Is that correct? Is that your conclusion that you from your
not
experience?
give accurate results? Not give accurate results.
Right. Okay. So I don't know. I'm not really sure about which companies you have the experience with, but we as TGT, we are specialized in identifying this particular case that if there is poor cement and you suspect behind casing channeling, we can identify behind casing channeling for you using noise. One of the biggest applications of noise for TGT worldwide is to identify behind casing channeling noise, and specifically of cases with poor cement. We have a long history of identifying there is behind casing channeling or like source of water through poor cement, and we have clearly identified in multiple of cases. I'm not really sure about the case studies that you're talking about, but from our side, I can like very confidently say that if there is flow through poor cement and it causes behind casing channeling, it will be identified using TGT noise log.
Excuse me, Mr. Abbas. So Ravin,
Yes.
for this well, I believe the noise log wasn't run to detect casing.
Correct.
It run to detect the tubing and ESP, as far as I see.
Yes, we didn't even go below the ESP pump.
Yes, yes. Yeah. So just to answer Mr. Abbas. So Mr. Abbas, for this well, this SNL even didn't pass below. The goal was to evaluate just inside the tubing. They didn't check anything outside it, as far as I understand from the Ravin. I'm correct?
You're right. You're right. You're right.
Yeah. Yeah, they didn't. The goal wasn't to check something. And Mr. Abbas' point is that
That means the below tubing shoe didn't check it, right?
yeah, because ESP I believe there is ESP.
Even have ESP. If you have tool, we can check. You have tool or not?
Yeah, white tool. No, I don't believe
No,
they have white.
I don't think they have white tool on this case. Most probably, I know where this case was happened. So the client was struggling with
If you
this
have white tool, you
ESP.
can check below tubing shoe.
You are right.
Yes, but not of the operators. They putting a white tool.
Okay.
And I have small comment on previous conversation.
Yeah, so just before just this is pulse 1 or different, because I don't see the 2D map, or this is pulse 3. Pulse 3, yeah, because there is no 2D map. Okay.
Yeah, I just want to come back to previous comment about like poor cement and acoustic performance. I don't think there is like yes, there is a link. If you have like poor cement, you will have like one type of acoustic data. If you have like better cement, it will be another type. But in same time, we're doing jobs worldwide. We're running SNL in open hole tools, whereas there is no cement at all. It's like just horizontal wells with horizontal section, and there is no cement at all. Yes, sometimes if you have channeling, it's one case, but I cannot clearly confirm that if you have like very poor cement, like SNL data, it will be bad. So SNL data based on acoustics, and it will be different physics in terms of channeling. Yeah, thank you.
Yes, from my experience in our field and in our wells, sometime or not sometime, many wells you have microfracture and fracture behind casing. Bad properties, but you have microfracture. If the bore is cement, we'll do confuse with our side. This flow come because the cement bore or because the microfracture. This is I mean. I agree with you. Many horizontal well no have cement. Our field no have cement in horizontal well, just perforated pipe, no cement. But if no cement, also we have microfracture and fracture in our formation. Sometimes do confuse for our side. This because no have cement or because have microfracture. This is I speaking about the noise log.
Thank you very much, Mr. Abbas. I totally understand your comment. So yes. I think it was covered on previous webinar. So I don't want to go deeply in details. So my point is whenever we're running noise logging, by the way, we're calling it chorus.
Yes, whenever for this case is very clear. This case because you check inside the tubing.
Yes, whenever we are running any acoustic logs, we are not only running one type of log. We're always combining with temperature and another sensor. So we have support from another sensors, and this one will give us full picture.
Sure.
Yes. So Valdan, just to introduce you to Mr. Abbas, he's the petrophysics manager for for CNOC company in Amara city, responsible on 3 fields, Bazargan, Abu Gharb, and Fekka. Okay, they have a lot of fields, a lot of operation there.
Thank you, Mr. Abbas, for your comments. So I'll just, yeah, thank you. So I saw 2 more questions. I'll take those 2 more questions. Are there any operational limitations for this tool, especially the wellbore fluid? So no, there are no operational limitations in terms of what is the fluid inside the borehole or what is even the condition of the well. Electromagnetic survey can be done even if the well is shut in or flowing, right? So I hope that answers your question. Jasim, thank you. Mr. Ali, is it possible? Yeah, sorry, Abbas, you wanted to say something?
No, I say thank you.
Perfect, thank you. So, Mr. Ali, is it possible to connect both tools together and run both as one go? And is that affect the line speed? Yeah, thank you for this. Is a great question. So, Ali, what we have usually do and what we recommend is to run both of them separately. So we do, like as you saw before, we do a run and hold, and we do the pulse as a continuous pass. And after that, we do temperature, and then we do noise in stations, right? But in some particular cases, like rig jobs, where the client is very particular to do it as fast as possible, we do the down pass with the pulse and up pass with the chorus. So in specific scenarios where there is a very high restriction on the time, we do it, we connect the tools and do it as one go, right? So it is, and is that affect the line speed? Yes, because if it's separately, the line speed during run and hold, we can do it very fast. But if we are connecting it in one go, the run and hold will be at 10 feet per minute or 15 feet per minute, and the up pass will be in stations, right? So I hope I answered your question, Andy. Thank you for your question. Right. So
there is one more questions, Mr. Rafen, regarding the wellbore conditions. Do we need to what you call it to clean out the wellbore from like a mineral deposit, for example, or asphaltene to have the accurate reading for this pulse tool?
Thank you, Lambert. This is a great question. So basically, this is one of the biggest advantages of electromagnetic technology compared to multi-finger caliper, where the caliper physically have to touch the internal diameter, right? To like very properly touch the ID and see if there is any metal loss and so on. So electromagnetic technology, it magnetizes the metal. So unless you have some electromagnetic deposits, you should not be worried about cleaning the well inside the well bore. Even if there is like mud deposits and so on, it will not affect because it just works on the principle of magnetization, and like mud has no effect of this magnetization. So the good part is that you don't have to clean the well before you log electromagnetic survey.
Perfect, thank you.
Thank you very much. Right, so I have one more case study. This is another interesting case study. We recommend it to our clients to understand the life cycle of the field, to plan the workovers and so on, is to do a time-lapse corrosion propagation monitoring. And a lot of clients do it very periodically to understand how the corrosion is progressing with respect to time, to see how corrosive environment are we working with. How can we plan the workovers? Which wells are more important for workovers? To understand if further workovers need to be done to increase the life of the well. So this is one case study in which we. So the first survey. So you can see from left to right. Here you have the well sketch with 3.5-inch tubing, 7-inch casing, and 9.5/8 casing. Here you can see in the first column, this is the thickness for 7-inch production casing from 2020 and 2017. So the green color is from 2020 and the blue color is from 2017. You can see that there is a metal loss increase. So in 3 years, there has been a progression of the metal loss. in not just the 9/5/8 casing, but also 13/3/8 casing. So in the 7-inch casing, the maximum metal loss increased from 13% to 19%. In 9/5/8, it increased from 58% to 69%. So once we do this study in equal intervals of time, we can assess how fast is the corrosion progressing, or probably there is no need to do this time-lapse corrosion monitoring at all, because we don't see the corrosion progressing so much so fast. So we can increase the monitoring time between the corrosion monitoring. So this is a very useful technique which is recommended to understand how the corrosion progress in the well, to understand the life cycle of the well and the field and so on, to plan the workover and so on. So this is also an interesting case study which I wanted to share with you to understand how the corrosion progresses with respect to time, right? So I would just like to summarize.
What software is this one? Your software?
It's our software itself, and we are just plotting the old and the new thickness together to come up with the conclusion for this.
Yeah, time lapse. Okay, thank you.
Yeah, time. So basically, just to provide a summary, basically what electromagnetic survey provides is a metal by metal assessment of multiple tubulars through a single tubing deployment. And it is independent of deposits in the wellbore. It has no scratch contact. It can assess the thickness behind scale. It is independent of the fluid type in the wellbore. It senses internal and external metal loss. You can use any conveyance, slick line, wire line, coil tubing, to understand the metal loss. And the best part, you can understand the condition of multiple tubulars by a single run. Yeah, so that's all from my side. Thank you for your attention and very interesting questions. I really appreciate your time. I hope I was able to provide value for your time. I really appreciate your attendance and your very valuable questions and great concentration in the program. Thank you very much.
We appreciate your effort. Vildan, have a question?
Yeah, thank you very much. Thank you very much, Vishnu, for this great presentation. I just want to add a few more words about few more application. It's not so major, it's not so general, but whenever we are working as a operator, sometimes this idea might help to you. One more additional application, whenever you are planning to do site track and you are planning in which area you will be doing the window, so you don't know the position of the colors of the second and third barrier. Whenever you are running such technologies, for example, Pulse 2, we can identify the colors of the second and third barrier of your casing. And in this case, you can plan your site track accordingly. And one more application, which is in my mind, we did job in Norway, if I'm not mistaken. The purpose of this job was to identify the centralizer, the position of centralizers in a 20-inch casing. So we did the job. We prepared SPE paper as well on this one. So we saved a lot of money to the clients because it was offshore operation, and the cost of this equipment and crew. So we make a big saving for them. This one, two more additional application for this one. Thank you.
Okay. Thank you so much, Vildan. Do anybody have any question before we conclude the session?
Yes, I have last question. Sorry for my question.
Yeah, please go ahead.
Thank you. Just I asked Mr. Havin if he used this tool sometime with the BLT or not. Because as you know, this is corrosion, I know, but you use it as a caliber. Sometimes using as a caliber case tool, right?
Right. Thank you, Mr. Abbas. Yeah, sometimes we do run it with the PLT because even though the application is different, sometimes
yes,
we do run it.
But according to the design for this tool, I check the speed for this tool, how to working good in the speed. For example, when run BLT, you have many speed, 10, 20, 30, 40, right?
That's right.
according to the BLT. If run this tool together with BLT, maybe different speed, different will affect the result for this tool.
Yeah, so what we do usually in such cases is that we decide, like initially either PLT records the data or we record the data even though we are in the same string. So we do our pass, and after that the PLT runs their pass, and we split the passes within the same string itself, and that's it.
Yes, maybe in the same string difficult. Run gamma ray CCL with this tool, because the benefit for or the advantage for this tool no have like XY caliber. Sometimes XY caliber difficult run with Y tool. Therefore, use like this or ETT or MTD or this.
Right.
Then you
Yes.
should separate, not the same run. Run different speed is difficult for result. This is my question.
It depends, right? If it's very necessary to run it in the single run, yes, we can combine. But if some cases it's separate, it's even better. It's like one tool, we know that the other tool is not affecting it, and this is the best way to go. But it's still possible to combine them if it's actually necessary. We have the connections and we can separate the passes, and that's it.
Thank you, Mr. Ravin, for your perfect
thank you,
presentation.
Abbas.
And
It's a
thank you
pleasure
for Mr.
speaking to
Mahdi.
you.
Thank you for
Most
all.
welcome, Mr. Abbas, and it was our pleasure to host you. I believe this is second time you attend, and we're hoping to see you always.
Thank you very much. Thank you. I am very pleasure.
Okay, it's our pleasure. So if anybody, if no question, okay, or if you have any question, you can email us. We'll send it to Mr. Ravin to answer. I'd like to thank TGT company, our attendees for this webinar. And just a reminder, we'll have another meeting on 21st of August. We'll announce this one in our LinkedIn. We'll create Facebook, WhatsApp for business, and Instagram maybe, and Telegram to have more marketing for next webinar. The next webinar will be with the EV company. Okay, they will discuss their new technology. Okay, and thank you all. We'll send the recording by email, and it will be published by YouTube as well.
Thank you. Thank you very much. Bye-bye.
Thank you.
Thank you very much for your
Thank you. Thanks everybody. And thanks,
you all.
Ravin.
Thank you. Bye.
Okay.